Hello everyone. So let's learn sequential models. In this session, I will guide you through an important concept in machine learning and deep learning, sequential models. These models are fundamental to solving problems where data is ordered and context over time matters, like predicting future stock prices, understanding language, or analyzing patient health trends. Let's dive in. What makes data sequential? Sequential models are specially designed to handle data where the order is meaningful, unlike regular models that treat inputs independently. Sequential models learn from patterns over time or sequence. They excel in tasks like time series forecasting, example like predicting future temperature. Next one is natural language processing, like translation, sentiment analysis. It also used in speech recognition for converting audio to text. Let's break down the types of sequential data. First one is time series data, second is text data, and last one is audio data. Time series data, this is the most obvious form. Examples include stock price, weather recording, electricity uses. Each data point depends on the one before it. The pattern evolve over time. Text data, in language the sequence of words determine meaning. For instance, the cat chased the dog is very different from the dog chased the cat. Third one is audio data. Audio and music are naturally sequential. They consist of vibration or frequencies evolving over time. In speech recognition, how a sound transition matters as much as the sound itself. Core concepts. To understand sequential models, we must understand the following concepts, like time steps, hidden state, state transition. In time step, these are the discrete movement in sequence, like hourly temperature reading or the position of each word in a sentence. Next one is hidden state. These are the internal memories the model maintained to store relevant past information at each time step. It updates this state based on current input and previous state. Next one is state transition. This refers to the mathematical function that govern how the model moves from one state to the next, depending on the new input and the old hidden state. These elements work together to allow the model to learn pattern across time. Next one is recurrent neural network. Recurrent neural networks are one of the earliest types of deep learning models built for sequences. They take an input at a time t, combine it with the hidden state from the time t minus 1 and produce an output and a new hidden status. However, RNNs face a major problem, the vanishing gradient issue. During training, gradients can become too small to effectively update the model, especially when trying to learn dependencies from long sequences. Despite this, RNNs have been used in language modeling, speech recognition, and translation tasks where understanding a sequence is essential. Next one is long short-term memory networks. To solve the limitation of RNNs, LSTMs networks were developed. The key innovation is gated mechanism that could the flow of information. There is a three gate: input gate, forget gate, and output gate. The input gate decides what new information should be stored. The forget gate decides what information should be thrown away. And the output gate determines what part of the memory is outputted. These gates allow LSTMs to retain long-term information, which is critical in tasks like time series forecasting, like predicting future sales, in sentiment analysis, for identifying the tone of a movie review, because they can remember important patterns from a far back in the sequence. Next one is gated recurrent units. In gated recurrent units are an optimized version of LSTMs. They combine the forget and input gates into a single gate and reduce parameters. This makes GRUs faster to train, less prone to overfitting on small data, efficient on resources, limited systems. They perform similarly to LSTMs in many tasks and are popular in speech recognition systems where fast learning is important. Also in video analysis, where each frame forms fast part of a sequence. Next one is sequence to sequence models. In these sequence-to-sequence models are powerful for tasks where both input and output are sequences. The encoder reads the input sequence and encodes it into a fixed length vector representing the context. The decoder uses this context to generate output on the element at a time. These models are essential in machine translation, like example English to French, summarization for turning a paragraph into a headline in chatbots and question answering systems. Next one is attention mechanism. While sequence to sequence models are powerful, they struggle when sequences are long. Attention mechanisms solve this by allowing the model to focus on specific part of the input when producing each output token. Instead of compressing all input into a single vector, the model dynamically attends to the most relevant part at each step. This leads to better accuracy, more interpretable models used widely in image captioning, where the model looks at parts of the image while generating each word. Also used in neural machine translation, which aligns source and target language parts. Next one is application across industries. Sequential models are not limited to research, they are transforming real industries like finance, healthcare, manufacturing, retail. In finance, for predicting stock prices and detecting fraud by analyzing transaction sequence. In healthcare, monitoring patient vitals in ICUs and predicting disease onset using electronic health records. Also in manufacturing, for predicting when a machine is likely to fail or identifying anomalies in production lines. Also used in retail, forecasting demand and analyzing customer behavior over time to personalize experiences. These models enable businesses to make data-driven productive decisions. Next one is future trends in sequential models. What lies ahead for sequential modeling? Like the transformer models in like BART, GPT are revolutioning, revolutionizing sequence tasks with self-attention, eliminating the need for recurrence entirely. They are faster and better at handling long-range dependencies. Also used in hybrid models for combining the strength of CNNs and RNNs to process spatial and temporal data together. Great for video or sensor data. Also used in real-time processing. As IoT devices and edge computing become popular, there is a push for models that can analyze data instantly without relying on cloud servers. Also used in ethics and bias. As a model makes decision in sensitive domain, we must ensure fairness, eliminate bias, and build interpretable systems. So sequential models are essential for understanding and predicting based on ordered data. We have seen how RNNs, LSTMs, GRUs, and attention mechanism work and where they are applied. The future is moving toward transformers, real-time AI, and responsible ethical modeling. Thank you. Thank you for your time.